I want you to picture the modern world's single biggest addiction. And no, it isn't coffee. And it's definitely not scrolling social media, though. We're all guilty of that. It's electricity. We are consuming power at a rate that is, frankly, staggering. I mean, if you look at the data, global demand didn't just grow.
It exploded.
It skyrocketed. We saw a jump of over 7% in a single year.
It's the invisible engine of everything we do. I
Yeah.
mean, from the data center hosting this file to your fridge to, all the AI models everyone is talking about.
Just eat electricity.
Constantly.
Exactly. But here's the problem, and it's a massive one. We can build more power plants, sure. We can cover hills and wind farms. But how do we actually move that power?
Right.
Building new overhead transmission lines, those huge metal towers, is incredibly expensive. It's ugly. Nobody wants them in their backyard, and the permissions take years.
It's a classic infrastructure bottleneck. You have the supply, you have the demand, but the pipe connecting them, the grid is fixed.
But here's the kicker. Placing new transmission lines. It's hugely challenging, it's expensive, and often politically impossible. It is the ultimate infrastructure bottleneck.
The problem isn't just building new capacity, it's really about extracting the hidden capacity from the wires we already have. And that's our mission today, to understand how operators are using new techniques to increase the current carrying capacity, or ampacity, of those existing lines.
And the key concept here, the big one, is dynamic line rating, or DLR.
Right, but we need to start with the core insight because it is a little counterintuitive. The capacity of a line, so how much current it can safely hold, is basically an active thermometer.
Okay.
It is hugely influenced by its immediate heating and cooling environment.
So you mean the temperature of the air, the angle of the sun, the speed of the wind, that kind of thing.
Precisely. We know high wind speed is a massive cooling factor. But what's fascinating in the source material is the impact of things we usually ignore, like rain.
Rain.
Yes, rain. Studies show that precipitation can dramatically boost a line's capacity because that sudden cooling effect just rapidly drops the conductor's temperature.
So you're telling me that a sudden downpour isn't just, a mood killer, it's actually an operational boon for the grid. The mission then is translating those real-time dynamic cooling effects into actual, safe, usable power.
That's the whole game.
Okay, so before we celebrate DLR, let's diagnose the flaw in the old system. We need to talk about static line rating, SLR. Why did we have those cripplingly conservative limits in the first place?
Well, limits are just non-negotiable for safety and for longevity. You have two main physical constraints.
Okay.
First, there's thermal safety. Heat causes wear and tear. You absolutely have to prevent the conductor material from annealing.
Annealing. What's that exactly?
It's basically premature aging or softening of the metal, and it comes from prolonged exposure to high temperatures.
That makes perfect sense. You don't want your infrastructure degrading faster than you planned.
Yeah.
What's the second constraint?
Public safety. And this relates to line clearance.
The sag.
The sag, exactly. When a conductor heats up, the metal expands, and the line sags closer to the ground. For instance, in the UK, a major 400 kilovolt overhead line needs a statutory minimum clearance of 7.6 meters from the ground.
Just to give us a sense of scale, what does 7.6 meters look like? Are we talking about the height of a two-story building?
More like a 2.5-story building. You have to ensure that at its absolute hottest, saggiest point, it's still far, far above any vehicle or structure that might pass underneath.
And SLR was the simple, brute force way to avoid that worst-case scenario.
It was. SLR was based entirely on avoiding the hottest, stillest, sunniest day possible, regardless of whether that day ever actually happened.
That sounds inefficient.
It's extremely inefficient. The ratings were calculated using the single worst conservative weather assumption. High ambient temp, minimal wind, high solar radiation, all happening at once.
Wow.
But here's the painful part. The industry standard, from bodies like CIGRE, requires that the static rating must be lower than the line's real capability with get this, a 99% probability?
Wait, hang on. So the rule is you must underutilize your assets 99% of the time.
That's the rule.
That feels like a mandate for intentional, colossal inefficiency built right into the physics of the system.
It is. It is the cost of conservatism. You hit on the core problem right there. It's the absolute price we historically paid for guaranteed safety. If you stick to that 99% rule, you can almost guarantee you won't violate that 7.6 meter clearance.
But it means that, by definition, 99% of the time, that line has more capacity than you are legally allowed to use.
That's it.
That's astounding. Can you give us some concrete numbers for these conservative conditions?
Sure, if you look at the ieee assumptions for SLR, they conservatively assume a wind speed of 0.61 meters per second. That's almost zero wind, a light puff.
Barely a breeze.
An ambient air temperature of 40 degrees Celsius, and solar radiation at over 1,000 watts per square meter. It is an extremely hot, still, sunny environment. CIGRE's standards are almost identical.
So system operators were basically designing the entire grid around a peak summer day in the desert, regardless of whether the line was actually running through, say, a windy, rainy mountain pass in Scotland.
And that's exactly why we need DLR.
Right. So if SLR is the rigid, old-school limitation, dynamic line rating is the necessary information upgrade.
It's the solution that converts that physical constraint into a dynamic resource.
So what's the simplest way to define it?
DLR is a real-time or near real-time calculation. It determines the maximum safe current based on the current weather conditions, not that single fixed historical guess.
And the benefit here is staggering. Our sources note that DLR deployments have shown capacity increases of anywhere from 20 to 70% over the old static rating.
20 to 70%. It's a massive operational gain.
It's like adding an extra lane to the electrical highway without laying a single new piece of cable.
And the financial implications are huge. It allows for safely integrating much higher volumes of renewable energy, and it just improves asset utilization across the board.
I saw a study that suggested if DLR was on just 1% of the world's lines, the savings would be in the millions.
Easily. This is really low-hanging fruit for grid modernization.
So, if capacity is a moving target, what's the math? How does the system actually calculate this max current in real time?
Okay, so the foundational principle for the calculation is achieving thermal equilibrium. It's a simple heat balance formula. Heat loss must equal heat gain.
That sounds like basic thermodynamics.
It is. The primary heat gains are joule heating, that's the current squared times resistance, I squared R, the heat from the electricity itself.
Like we said, your phone charger getting warm.
Exactly. And the other is solar heat gain from the sun. The primary heat losses are convective heat loss, mainly from wind moving past the conductor, and radiative heat loss.
And DLR just solves that equation constantly.
Constantly. It uses real-time measurements of wind, temp, and sun to constantly solve that equilibrium equation for the maximum safe current, for I.
Since DLR turns the weather report into an operational metric, let's deep dive into these environmental variables. What's the biggest lever utility operators can pull?
Wind speed, hands down.
Really? That dominant?
Oh yeah. Convective heat loss is the single most important cooling factor. It typically accounts for almost 70% of the total heat loss when the conductor temperature is above ambient.
70%.
The faster the wind blows across the conductor, the more heat is stripped away and the higher the line capacity goes.
So wind speed is the superstar of cooling.
Mm-hmm.
What about ambient air temperature? That seems like an obvious secondary factor.
It's an obvious factor, and it has a very clear inverse relationship. Colder air means higher ampacity.
Right.
And the impact is easily quantifiable. We can use the UK seasonal data from the research. The average temperature difference between summer at around 14 degrees Celsius and winter at around 3 degrees.
Okay.
That temperature difference alone typically results in a 73 ampere current difference for a standard 400 kV overhead line.
73 amps, just for the change of seasons. That's essentially free bonus capacity that's available just because the air is cooler.
It is. And then you have the heat gain side, primarily solar radiation. Solar irradiation is a heat gain, so it's inversely related to ampacity.
And that peaks midday.
Maximum solar heating is midday, which tends to be the worst time for capacity, all other things being equal.
And let's revisit the rain, the precipitation. How is that factored in?
Rain provides a massive instantaneous cooling effect. It's far greater than standard convection alone. A study observed the effect of heavy rain. I think a rate of 9.2 millimeters per hour was mentioned.
Wow.
And they noted the conductor temperature just dropped significantly, sometimes by 60% of the previous peak, before slowly rising again after the rain stopped.
So it's a turbo boost.
The turbo boost, exactly. A transient one, but very powerful.
Okay, so when operators implement DLR, they rely on calculation models. The sources mention two big ones, ieee and CIGRE.
Right, they are the two standards guiding the map.
What stands out when you compare how these two approaches handle the calculation in real time?
What's fascinating is that while the final outputs, when you average them out, generally differ by less than 1%.
They're pretty close.
On average, yes. But their inherent methodologies and sensitivities vary wildly. ieee tends to be viewed as more accurate, but computationally it is much more complex.
Complex how? Give me a concrete example.
Okay, take solar heat gain. The ieee standard uses these complex formulae involving geographical information, latitude, time of year, solar time, all to calculate the exact angle of the sun and the conductor's absorption.
So it's very calculation heavy.
Very. CIGRE, on the other hand, relies much more directly on simple, localized, real-time sensor data to approximate the solar heating.
So one is calculation heavy, the other is sensor heavy.
It's a trade-off, absolutely.
Are there conditions where this difference in complexity leads to a major divergence? A scenario where one model says it's safe to run 1,000 amps and the other says 1,500.
Absolutely. The key divergence appears at very low wind speeds.
The high-risk conditions.
Exactly, less than half a meter per second or near zero wind. In these crucial conditions, the calculated convective heat loss shows the largest differences between the models.
And what does that mean in terms of?
In one specific analysis, the difference in the estimated maximum current between the two models was over 900 amps.
900 amps. That is a huge operating gap based on slightly different math.
It's a massive difference.
Wow. Speaking of real-world data and complexity, let's look at that Edinburgh case study. Using 2019 weather data, they uncovered what looks like a genuine paradox.
They did. We established earlier that the physics dictates capacity should be highest in winter and lowest in summer, because of the cold ambient temperature.
Right, colder is better.
But in Edinburgh, the maximum average current was observed in July, a summer month.
July.
Despite July having the highest average temperature compared to the winter months.
So the rule of physics says winter should win. But the Edinburgh data says July. If you were just looking at the temperature data alone, you'd assume the utility was running the line way too hot, doing something very risky.
You would, and this is the perfect illustration of DLR's value. It shows the complex, interconnected dominance of all the variables.
So what resolved the paradox?
The data revealed that the maximum average wind speed for the entire year also occurred in July. It averaged 6.18 meters per second.
So wind was the silent assassin of the temperature effect.
Exactly that. The high average wind speed provided so much convective cooling that it completely overpowered the negative thermal effect of the slightly warmer ambient temperature.
It just shows you that the line's capacity truly is a dynamic resource, and wind is often the dominant factor, overriding what you'd expect from the season.
It proves it in the real world.
So what does this all mean for the grid of the future? I think the core takeaway for you, the listener, is that DLR transforms the perception of line capacity from a fixed conservative constraint
into a dynamic, measurable resource.
Yes.
And it's vital for system awareness, for reliability, and critically for safely integrating renewable energy.
Right, the wind farms.
Think about it. When the wind is high, you are generating massive amounts of power. But that same high wind is simultaneously cooling the transmission lines, allowing them to safely handle the extra load you're trying to inject.
So the system organically handles its own output increases.
Yeah.
It's an elegant, synergistic solution using existing infrastructure and just adding computational intelligence.
It is. And if we connect this to the bigger picture, the analysis confirmed that thermal resistance has a remarkable effect on loadability of the line.
Okay.
Since resistance is just inextricably linked to the conductor's temperature, the ultimate challenge isn't just measuring capacity now, but accurately and locally forecasting those key meteorological parameters.
Forecasting wind, temperature, precipitation.
In the short term, yes.
Right, because if you know the wind is going to pick up in the next hour, you can safely ramp up generation now, avoiding unnecessary curtailment of renewable power.
Precisely. That need for ultra-local, short-term predictive capability. That's the next frontier. We need that weather forecast to be specific to the next kilometer of transmission line.
And this raises an important question. What unforeseen technologies, maybe hyper-local atmospheric sensors every few kilometers, coupled with AI weather prediction models tailored specifically to transmission corridors, what might we need to deploy universally to achieve that ultra-precise predictive capability across the entire grid? That's something to mull over the next time you hear a wind gust.
A fascinating problem for the engineers of tomorrow.
We hope you enjoyed this deep dive. We'll see you next time.